Hi friends, welcome to this video. So in this video we will go through DoubleUNET, a deep convolutional neural network for medical image segmentation. We are going to implement DoubleUNET in TensorFlow using Keras API. So let's get started. Here is a small slide on the DoubleUNET and here's the original diagram. So if you want to have a look at the original paper, you can check the link given in the description. You can read the paper. But for this video, this slide is enough. There are basically two UNET, that is network 1 and network 2, used sequentially. First is a pre-trained UNET as it uses VGG19 as the encoder, and second is a non-pre-trained, does not contain any pre-trained structure. So image goes to encoder the encoder 1, that is VGG19, follows the ASPP, then the decoder block. So the decoder 1 uses kept connection from encoder 1 only. We get an output 1 here. Output 1 is a binary mask, so it multiplies with the input image. So the output 1 acts as an attention here, so it enhances the important region in the image and suppresses the region which aren't required, because the output is a sigmoid. So what sigmoid is, it outputs value between 0 and 1. So if it is near to 1, it is more important. If it is near to 0, this means it is not that much important. So it's basically apply attention over the input image. So this mask acts as attention mask. Okay. Then this attention input image goes to the encoder 2, which is basically from scratch. Then again ASPP and then decoder 2. So decoder 2 takes kept connection from both encoder 1 and encoder 2. So it basically takes feature from both a pre-trained encoder and a non-pre-trained encoder. So it's kind of an advantage for it. Okay. Then we get the output 2, and again it is also a sigmoid output. Then we have our final output. So that's basic architecture. Okay, so in between it contains ASPP, that is Atrous Spatial Pyramid Pooling, and it contains Squeeze and Excitation. Squeeze and Excitation is basically a channel wise attention mechanism applied to the convolution layers in the DoubleUNET architecture. So we're gonna first implement the Squeeze and Excitation, then ASPP, then we'll move on to the rest of the component. Okay, so let's first start with Squeeze and Excitation. So I've already told you it's a channel wise attention mechanism. Here I have already imported all the layers and the thing required. Now let's define squeeze excite block. Okay, let's give a space here. Okay, so it takes the inputs and ratio value. So ratio is 8. INIT inputs. We're gonna make a copy of the original input. Channel axis. Channel axis is -1, basically last channel. So the format of input is like batch size, height, width, and the channel. It's not like a PyTorch version where we have batch, channel, height, width. Okay, so that's why channel axis is -1. Now what we need to do, so we're gonna first create a pooling operation. So we'll perform a global average pooling over the input image to suppress it, basically to squeeze it. Okay, and to have an embedding, so to have a whole representation of the input feature. So we're going to suppress it using global average pooling. Let's say SE is equals to global average pooling 2D on the input, that is INIT. Okay, it's full mistake. Okay, then we're going to reshape it, because now the features are like, let's say if the input is like, let me give an example here, is like B, and height is, let's say 128, width 128, and the number of channel is, let's say 32. So it's of shape like B, 32. Okay, so we have a 2D representation here, but we need to reshape it. Okay, so we're going to reshape it to this, let's say B 1, 1, 32. So we're going to give it a height and width of 1 pixel each. Okay, so let's do that. So for that we need to know the feature, the number of filters it has. So let us first have filters. Filters equals to init.shape, and we have channel access. Now we're going to say the shape, which you need to modify it, 1 comma 1 comma filters. Okay, so we have the shape also. Next we're going to reshape it. SE is going to be reshape, SE shape. Okay, input is SE. So next, here is the squeeze operation. Okay, we get a in representation of the whole feature, and we have to reshape it. Next we're going to perform excitation operation. So it's basically two dense layer where feature are first compressed and then enhanced. Okay, dense layer, filters divided by ratio. So this ratio variable basically define the amount of compression, the amount of the how much we want to reduce the amount of features, the number of features in the dense layer. Activation going to be reloop. Okay, and we're going to say use bias is equals to false. Okay, and input is SE. Then again a dense layer, SE dense. So we're going to make the number of filters to the original filter, that is 32 for example we have said, and here activation is going to be sigmoid, and use bias is going to be false, and input is SE. So now we have sigmoid as output, and I've already told that it will contain value between 0 and 1. Okay, so 0 means it is not much important, 1 means really important. So if I multiply anything by 1 it remains same, but if I multiply anything with 0 it becomes 0. So what it does, it suppresses the things which are not important. Okay, the features which are not much of that important is suppresses those features. So now we have this attention kind of thing here. So we're going to multiply it with the original input. Okay, multiply original inputs. Okay, with the SE, the attention map. So it's basically a channel wise attention, because you can see the shape is like this. So this is the shape here also. Okay, so that's why, because it is applied channel wise, not whole image. So we need, why do we need squeeze and excitation? Why do we need a channel wise attention mechanism here? So my reason is that, because as you know we have a convolution layer. Let's say we have a convolution layer and it has 32 number of features, 32 the number of feature channels. So it treats every feature channels the same, but that isn't a require every time, because maybe sometimes some feature maps are important and some are not, some channels are important and some are not. So this squeeze and excitation provide a channel wise attention mechanism. So what it does, it suppresses the features of those layers, of those feature maps, or the number of filters which are not much important. If it is important it remains the same. Okay, that's why we need squeeze and excitation. So that's why it enhances the performance. Okay, so this is all about squeeze and excitation block. Next we have our ASPP block. This is really important. Let's define ASPP. It take X as the input and number of filters. Okay, so what does ASPP do is basically apply dilation rate, or we can say it's Atrous convolution. So Atrous convolution basically use a greater field of view to capture much more information. You can see here an image which show you the number of dilation rate and its effect on the input, how much greater broad range information it can extract. So let's start the code. So let's extract the shape first. Okay, so y1 is average pool 2D, and I think I haven't called it. Okay, so let me just call it here, average pool 2D. pool size is shape 1 and shape 2. Okay, and input is x. Okay, then we have y1, and we're gonna apply convolution operation. Number of filter is already given. Convolution, so the size of the kernel is 1 by 1. Padding is equals to same, and we're gonna y1 here. Okay, so next it's gonna follow the batch normalization and then a reload activation function. Y1. Okay, then a reload activation. Activation is equals to reload. Then again we are going to upsample it. So here no dilation rate is provided. It's not the Atrous convolution. We just taking the input feature map, creating an average pooling map of it, and again upsampling it to the original shape using bilinear interpolation method. It's basically first we have image, we downsample it, then we upsample it. It's simple. Upsampling 2D. So I need to call this method also. Let's go down. Shape 1, shape 2. Okay, then we have the interpolation method. Bilinear, and input is going to be y1. Okay, so let's do one thing. Let's test these function likewise. Okay, so first of all we need a variable. Let's say x as input. Can you take numpy tf dot tensor of shape equals to, let's say, base size 8, height 128, width 128, number of filter 32. I hope it would be fine. Then we have ASPP. Okay, x at input and 64 as number of. So let's spin the shape of y1. Okay, some messages from the TensorFlow. Okay, TF is not defined. Okay, we haven't defined the TensorFlow. So let's define it at the top, the beginning. Import TensorFlow as TF. Next, it has no argument as shape. Okay. Okay, I think I need to do it. It should be like TF dot once, like we do in NumPy. 8 by 128 by 128 by 32. Let's see, or I check on the Google. So I think it's right. It's right. Okay, so you can see we have a shape, and this is we have printed here. Yeah, the y1. So it is the exact same shape, 121. So we're gonna print it here also. So what happened here? We're gonna see. Okay, so you can see the shape changes to 8, 1 by 1 by 32. Then we again upsample it and increase it to 128 by 120. So that's what happened, and we also change the number of channels. Okay, so next we're gonna have some dilated convolutions. Okay, so we're gonna define some convolution layer. Let's say y2 on 2D. Okay, number of filters as filter, Kernel size is 1 by 1. Dilation rate is 1. So dilation rate 1 is basically the normal convolution operation. There's no difference. Padding is equals to same. So we're going to say use by is equals to false, and input is x. And here we follow the batch normalization and the reload activation. So I'm going to copy it and change the variable names y2 x. Input is y2 and y. Okay, so this is a convolution layer with 1 by 1 as kernel size and a dilation rate 1. So if you're going to specify that, if you just remove it like this, it's going to remain the same. There's no difference in it, just because here dilation rate is 1. 1 doesn't change anything. So we're going to apply next dilation rate, the next convolution layer. We're going to say it y3. So let's first change the name of the variables. y3. Okay, so now we're going to change kernel size to 3, because here we're going to apply a 3 by 3 kernel size, and dilation rates we're going to change it to 6. Rest everything going to remain the same. Okay, now it's time for x4, changing the variable. Okay, y4 and y4. Now the dilation rate changed from 6 to 12. Okay. Again, one more time, the last time. Here we're going to change the variable name to y5. Here y5. Note the dilation rate, the variable name and dilation rate to 18. Okay, so now we have applied 4 dilation rate, that is 1, 6, 12 and 18. So it's going to capture broad range information. Okay, now we're going to concatenate these. y1, y2, y3, y4, y5. Okay, then we're going to apply simple 1 by 1 convolution layer, and we're going to copy it from here. Let's say y and y, and input is also y, because y contain a concatenated information of y1 to y5. Now this concatenated feature map passes through a 1 by 1 convolution. Okay, and it's gonna return y. Okay, return. So let's say it return y. So what's the output feature map? Print y dot shape. Okay, so you can see the output feature map is 8 by 128 by 128 by 64. That's the output feature map of ASPP. Let's do one thing, write one more line here so that we don't get these unnecessary TensorFlow lines on the terminal. Okay, now we're gonna run it again and see no unknown, no more TensorFlow lines, direct point to point. So we need this shape, we have printed this shape, none other. So it look much more clean and easy to see. So these are the two functions which we have created now, that is Squeeze and Excitation and ASPP. Now let's move back to the slide. Okay, first we have the encoder one. So encoder one is a VGG19, a pre-trained VGG19. So we're gonna create the encoder one function. Okay. So here we're gonna move to the encoder, dev encoder one. We're gonna take the input layer, inputs. Okay, so next we need to define the model, the backbone or the pre-trained architecture, VGG19. You can use any other architecture, but in the original paper they uses VGG19, so I'm gonna use the same. include top is equals to false. Next, weights are important, that's why we are using it. And one more advantage is also there, which I feel is an advantage. I'm going to show him. Just let me complete this variable. Input tensor is equals to inputs. So if you're going to go back to the slide and we're going to see the architecture. So you can see the architecture is really deep. You can say 2 units stack on top. So this last, so the, not last, just last from, if we start from the output and goes up during back propagation. So this VGG, the encoder one, VGG19, the weights here aren't going to receive much of the gradients. Okay, so that's why its pre-trained nature helps it, and also the skip connection also going to help it. But still, it's really deep. It's at the top, at the beginning of the architecture. So we aren't expecting it to get much of the gradient as compared to the decoder 2 layers. So that's why it is also an advantage for it. So we have this VGG19 model here. Okay, so now, so we need skip connections also from this. Okay, skip connections. So now we're gonna print model.summary. Okay, because we need the names of the layer. What is the names of those layers from which we need to extract the skip connection? Okay, and then we will get the output also, but let's go through this. Let's see, the shape is 256 by 256 by 3. Encoder 1x. Okay, should we include not to, should we include top? Okay, let's see. It should be inputs, so I know what I have done. So this x should be like inputs, should be like 256 by 256 by 3. This won't work here, so we have to specify it this way. Inputs should be input, not inputs. Again a mistake, run it again. So mistakes are common for any programmer. You can see now we have the summary of the VGG19 architecture, and we can easily extract information from it. So we need skip connection, that is activation function output. Okay, so if we just go back to slide and see the structure. So we need the output. So we have this block 1, block 2. So like this, we need the output layer, output of the layer before the max pool. Okay, so this is max pool. We need first this block 1, con 2, and its shape is 256 by 256. So let's copy these. Next is 128 by 128. So this is block 2, con 2, and is also before max pooling. So remember, don't go for max pool features. Okay, these max pool features, so they are basically, they have half of the information which we can get from the their previous layers. So getting much, so we need much information as we can get. Next is 64 by 64. So block 3, con 4, and we need the last feature map for the skip connection, that is 32 by 32, block 4, con 4. Okay, I already have a video on VGG19 UNET. If you want to watch that, click on that I button, or you can check the description for that video. I hope you just watch that video. After this, you're gonna get much better understanding how we can build VGG19 UNET. Okay. So now we have all the 4 skip connections from the encoder, and we also need something more. Let me write it just now. Output equals to model dot get layer, name of the layer, then output. So here we need 8 by we have 16 by 16, not 8 by 8. block 5 con 4. So now we can remove this summary. So we need to extract the skip connections, the feature maps. We can say from name in names, and we have already defined the skip connection list. Here we're going to save those features. So skip connection dot append, say model dot get layer name dot output, and we're gonna return output as skip connection. Okay, so the encoder one is done, part is complete. Now we're gonna go, where we gonna go? So what is it? Okay, let's what close without saving. Okay, so we're gonna do the next one. We need to go to the decoder 2. So here's the part of the decoder 2. So you can look at the diagram. We have skip 1, then we have input, then upsampling, then we perform concatenation, then a simple convolution block which have two 3x3 convolution, each followed by batch normalization and reloop. You can see the architecture of the decoder 1 block is same as UNET, except that it uses bilinear interpolation instead of transpose convolution and squeeze and excitation at the last. Okay, and it receives skip connection feature maps from the encoder 1. So let's follow these things and build our decoder 1. Okay, def decoder 1. So you take inputs and the skip connections. Let's define number of filters here. 256, 128, 64 and 32. So we have skip connections. Okay, starting from size 256 by 256, then to till, and we have 256 to 128, then 128 became half, 128 half is 64, then 32 by 32. So we need to reverse them and start with 32 by 32, because this input is going to be this output, and the shape of this output is 16 by 16, and this 16 by 16 goes through this upsampling layer, became 32 by 32. So that's why we need skip connection to be reversed. X is equals to inputs. Okay, we need to write the con block also. Okay, we will write after this part. X is equals to upsampling. Okay, so we have 2 by 2 upsampling, interpolation is equals to bilinear. Input is X, then we're going to perform a concatenation between the upsample feature map and the skip connection. Okay, what I'm doing, I just missed the loop statement, and I'm just writing should be we should have to enumerate over the number of filters. Now it's in the correct form. I'm just imagining that I've written the loop in my brain. I have noted written there. Then we have the con block. We're gonna write this function con block, X as the input and F as the number of filters, and it's gonna written X. So the decoder 1 is complete. Just we need to write this con block function. Let's go here after the ASPP. Define con block. We take input X num and the filters. So let me copy this from here. Let's change it to X. So filter and convolution is 3 by 3. Dilation rate 1 doesn't matter, so we can remove it or just remain same. We're gonna remove the use bias, and here input is going to be X, then X, X. We're gonna repeat this combination and return X here. So this is simple convolution block which containing convolution layer, a batch normalization and activation, and again same layers repeated in same sequence. So we have encoder 1 and decoder 1. So let's start building our main architecture. Okay, the double unit. Let's say build model, and we're gonna have input shape. Let's say inputs is equals to input shape. So we're gonna have output and skip one from the encoder one, and it take the inputs. Okay, then the encoder is finished, then we're gonna have the ASPP in between. Okay, I've forgotten the ASPP X, and we're gonna say number of features as 64. Then we're gonna have the decoder 1. It takes the output of ASPP and skip 1. Okay, so this is, so now we should have this decoder 1. Okay, so now we need a mask. We haven't got the mask, the binary mask. I think we need an output block also. Okay, let's create one more thing called output block. Output block. Okay, it take inputs and give us a binary mask with channel 1 on 2D 1, number of kernel size is 1, number of features is 1, padding equals to same, again extra comma, remove and input is going to be inputs, and activation, let's say activation is going to be sigmoid. And input is X, return. So we have this output block. It take the input feature map and convert it into binary mask. So we're gonna now have the output block, and gonna take X. So now we're gonna print the shape of this output 1, and I assume the shape should be of 256 by 256 by 1. Input shape. So this is the input shape, 256 by 256 by 3. And let's say build model, give it input shape. Now let's run it. Okay, X is equals to inputs. This is incorrect. Again, how much mistake I've done here? Really much, very mistakes. Okay, so finally, after correcting a lot of mistakes, we have our mask, the output 1, that is 256 by 256 by 1. So now if we go to the slide and we go to the architecture, now the input for the encoder 2 is output 1 multiply with the inputs. Now let's do that. Say X is equals to inputs multiply with output 1. Okay, now like this we need to prepare encoder 2 and decoder 2. So let's start working on them. The encoder 2, encoder 2. So encoder 2 takes the input feature map multiply with the mask. Next with number of filters 32, 64, 128 and then 256. So these are the number of filters. Then we have a skip connections which you need to extract from the encoder. So let's say X is equals to inputs. We're gonna have a loop here, and this time I won't forget I have an enumerate. Last time I was a little confused, so I just make mistakes. Next we have x is equals to conv block, x as input, f as the number of filters, then skip connection dot append x. The output of convolution block act as skip connection, and then it is followed by 2 by 2 max pooling. Max pool pooling, 2 by 2 max pooling. Input is x. So like this, we're gonna say out return x, the last the output of the last mix pool block, not mix pool block, the max pooling layer, and then we have skip connections. So encoder 2 is ready. Let's incorporate it in the build model. X and skip 2 equals to encoder 2, and input is x. Now let's print shape of x. Okay, the input is 16 by 16 by 256. Okay, now we need to write the code for the decoder 2. The code is basically same with few changes in the decoder 1. Let's copy it, and if you see, so let's go to the slide. First we need to go to the slides also. So this is encoder 2 we have built just in normal thing. Okay, we need to add squeeze and excitation also, and we have forget that. Okay, let's do that. Do we need to add to the okay, and we have to add it to the that encode also. Okay, let's correct our mistakes first. So we're gonna add squeeze and excitation to the convolution block only. It's gonna work automatically. We need not to add it anywhere else. Phases. Okay, here. So we're gonna say x is equals to squeeze. I just forgot this block, squeeze and excitation. I don't think it take anything else, so it is included automatically in every other convolution block which we have used. Okay, so now we need to work on the decoder 2. Okay, so we have this encoder 2 is ready. Then we have to work on the decoder 2, just same as decoder 1, just that it contains skip connection from both the encoders. You see the architecture, this is a decoder 1 and this is decoder 2. They are just minor difference. The overall architecture of decoder 2 is same as of the in decoder 1, except the second skip connection. Okay, it receives skip connection from both, skip connection feature from both encoder 1 and encoder 2, so it which help in boost the performance, as we know, because it receiving much more information. That's why there's a boost in performance. Okay, so we're gonna copy a decoder 1 and we're gonna paste it at the bottom, and we're gonna rename some things, like rename it to decoder 2. And we have now two skip connection which we need to manage. Let's say skip 1 and skip 2, and here we need to add it to skip 1 and skip 2. Okay, so everything remains the same. We have first we upsampling, a 2 by 2 bilinear upsampling, then we have concatenation of the upsampled feature map skip connection from encoder 1 then encoder 2. Then we have a convolution block with 2 3 by 3 convolution layer and a squeeze and excitation block. Then we have the output. Okay, so the decoder 2 is also ready. We need to incorporate it in our build model function. So let's say x is equals to decoder 2, and we need to add ASPP. I always forgot some major component of this thing. 64. Okay, then x, here I have skip 1, skip 2. Okay, so we have the output of a decoder 2. Now we need output 2. Output 2 is equals to output block x. So now we have both in both input, output 1 and output 2. Now let's do a concatenation of on both outputs. Output 1, output 2. Now let's build a model. Call the model class, give it inputs, input layer, and the outputs, output. Return the model. Okay, so the model is complete. And let's model and print this summary and check if everything is working fine. Okay, so we can assume everything is fine, but still something is missing which I haven't checked. And here skip 2 need to be reversed because skip 1 is already reverse. Okay, so finally we have architecture ready with a lot of mistake and lot of work. Not that much work, but especially a lot of mistake, and I'm sorry for those silly mistakes. But it's like if you don't make mistake, you don't try. You try, then you make mistakes. So just keep trying. You will make mistake, you will correct them. So let's go to beginning. So the initial input shape is 256 by 256 by 3, and it goes through the entire architecture, and we get the output mask, two output masks, that is 256 by 256 by 2. Okay, so these are the two output masks. So here we have output, here we have the input layer, then we have the output 1, then we have the output 2. Okay, and we finally get our model ready. So this is all about the double unit architecture. So I hope you just learn a few more things in this video, and if you learn, then please hit the like button and the subscribe button and wait for more such content. Thank you. Have a nice day.